Hi everyone, welcome back. This is Anthony Bober, and this is going to be an update to part one. In part one, let me find it. I found the gradient and I used closure. I used a function within a function here to actually calculate what the gradient is. Um, but I wanted to make an update video for this because for part one, what we wanted to do was use closure to calculate the Jacobian of the central helical curve, not the gradient. Now, in the example I used in the first video, um, the gradient was technically the same thing as the Jacobian because I used one function. But if we were trying to use that for multiple functions, that my my get gradient and gradient functions here would not actually work for that. They would only work for gradient or for one function. So I'm going to basically kind of repeat this process, but just to get for the Jacobian instead of the gradient. So first thing I'm going to do is define function, and we'll call it get gradient, get Jacobian, right? And we'll just call it get Jack. It'll take in our function f, and then I'll specify a function in that function, and I'll call it Jack. And it's going to take in a value, we'll call it x naught, and we want to also calculate an h value. So we'll call that h, and I'm just going to go ahead and specify what h is. It's going to be 1 times 10 to the negative 8th. Put a colon here. Now the first thing we actually want to do is we want to change x naught to be an array. And what I'm going to use for that is this called numpy.atleast1d. It will convert our input to an array with at least one dimension. So we're just going to be changing x naught into an array. The array will be called x naught, so np.atleast1d x naught, and I'm going to make a variable f naught, and it's going to be the same thing, at least 1d, and it's going to be f of x naught. Okay, and then I want to create we'll call this j for our Jacobian, and I want it to be an array that's as big as x naught and f naught, but I want to be updating this as we go, so I'll just give it zeros. And it's going to be as big as f naught, so f naught dot size and x naught dot size as well, and I think that should be it. Now what we want to do is iterate for every x value. So for every value, we'll call it I in range x naught dot size. So for that many values, however big x naught is, the first thing we want to do is create a new variable called x, and what we will use x for is to store our x variables plus h. So x will be a copy, np.copy, of x naught, and then what we will do is for the ith value in that array, it will be equal to that ith. I don't know if ith is a thing. It'll be that I value in x naught plus h. And then what we will do is we want to update our j with the x. So we will say f of x minus f of x naught, which actually in our case this will be just be f naught, because up here we said f naught will be all of the f of x naught values. So this is going to be f of x, and in this case remember x is equal to basically x plus h. So this is f of x plus h minus f of x all over h. And then actually what I want to do is, since there's multiple functions within this Jacobian, I want to specify what index of the array to actually change. So I will go ahead and do that. And this should take from the first index. So we'll specify that as 0. The first index of the array will go into the ith index of the Jacobian. And then that should be it. We will return j for our jack function. And then for our overall getJack function, we will return jack. We'll shift enter. And then I'm going to go ahead and test this. So I'll call this jack1 equals get jack, which is the function we just made. And I'm going to use a lambda t for our curve, which actually, let me scroll up here real quick. So curve is right here. So this is our curve function. It takes in t, r, m, z, and curve actually is a parametric function made up of x, y, and z, which are 3 functions. So in the case of this example, 3 functions, the gradient wouldn't work for this. So we will have to use the Jacobian to actually get that. So this is what curve is, and using lambda t, I will specify what r and mz are. And then it will plug in the t values. So say r equals r, mz equals mz. And I will say jack1 at 0.0. Cannot interpret 1 as data type. Let's see, what is the issue here? I may need more parentheses. Oh, perfect. Okay, so it tells us that our Jacobian is 0, 3, and 0.4. And I'm actually going to check this with the function I used at the very end of part 1 called jacks.jacobian. So I'll say jack2 equals jacks.jacobian. And actually, I'm just going to copy and paste this. So jack2 equals jacks.jacobian. Same exact function. We're just using jacks to do it rather than the function I made. And then we'll say jack2 at 0. And it tells us it's 0, 3, and 0.4. So as we can see here, the closure gives us the same answer as using jacks.jacobian. So that was using closure to calculate the Jacobian. Thanks for watching.